Welcome to our lecture on fluorescence and phosphorescence. We are going to mostly look at lasers here. So this is a picture showing some laser beams. Now we see laser beams a lot in movies, and in movies, what you focus on is, ooh, look at that beam. You can see that beam. And in this picture, you can see the laser beams. But you know what? Lasers are light traveling through the air. And we typically don't see light traveling through the air. So the fact is, a laser you typically don't see. You have to have something that is scattering the light off of it as the light goes through the air. So now if you have a really intense laser, maybe you'll be able to get some scattering that you can see from the actual molecules of air, the nitrogen primarily with oxygen. But more often, you're only seeing scattering off of the dust and stuff in the air. So when I go out for astronomy, I have these green laser pointers, and you see this flickery light going up the beam because what you're seeing is that green light being scattered off of dust particles and stuff in the air as it travels through the air. So to see an actual picture like this, you're going to need to have some kind of cloudy air. So if you actually go to a laser show, they're going to do something to give you some cloudy air, some water droplets. So you'll get a lot of scattering off of those water droplets. And then you can see where the laser beams are traveling through the air. In this case, the laser beam it's bouncing off of a mirror here and then going down different direction. The laser beams travel in straight paths, well, because of the ray nature of light. But you say, well, I mean, the ray nature of light, when I look at a light bulb, the light's going in all directions. A laser is designed to give us a collimated beam. I know my first letter looks like a G instead of a C, so I'm going to rewrite. Collimated beam. That is, you have parallel paths for all photons. Now, it's not possible to make a perfectly collimated beam, but we'll look at the design of a laser later in this lecture to see why laser light tends to be collimated. Another important feature about lasers is that lasers are monochromatic. That means they have just one color, or if you prefer, one wavelength, because we usually talk about the wavelength of a laser, or one frequency. One color, one wavelength, one frequency. If we're talking about the laser going through air, those all mean the same. If the laser beam goes from air into water, we know that the frequency cannot change. The color is going to stay the same. So really, we should tie color and frequency together, and the wavelength is going to change when it goes in water. And then finally, one more thing, and this last one is probably the most important. It's coherent. Coherent. When you think of coherent, you think, well, that's something I can understand. But what it means is it's sticking together. That means that all of the light is in phase. So remember when we were talking about the wave nature of light, we were talking about phase relationships. The light in the laser beam is all in phase, so each of these things is oscillating together in the same time and location. They'll all be max, and so on. That's an important aspect to laser light. It has to be monochromatic for it to even be possible to be coherent. And now, if we're going to be really, really strictly honest, we have a wave train that's coherent. So you might have, a few kilometers long of the light beam, which in time translates to not that long, that is all coherent, and then it'll switch and have another wave train that's fairly long. But if your wave train is very long, as far as you're concerned, the whole thing could be considered coherent. So these are the properties of a laser. Now let's get into the lecture. First, fluorescence. Fluorescence is cool. Back when I was a kid, we used to love to have black lights. and then things would glow in the black lights. Well, a black light is a fancy term for an ultraviolet light. Our eyes can't see ultraviolet, so we don't see the light coming from a black light. But it's giving off ultraviolet light, which, let's be honest, this can damage your vision if you look into ultraviolet light. You can damage the cornea with that UV light. But you have ultraviolet light. Now think about energy. Energy equals HF. Ultraviolet is higher frequency than visible. So if it's higher frequency than visible, then that means it's higher energy photons. So you have photons, particles. So we've just shifted. When I was talking about coherence, that's a purely wave thing. There's no particle action in phase. That's all about a wave. But now I've shifted to talking about the energy of a photon, the particle of light. And so you have this light with high energy, and when it hits something, like in this picture, when it hits that little scorpion, that light can be absorbed. And so you have, the energy level of whatever atoms are in the carapace of the scorpion, and the ultraviolet light might excite it up to that level. But of course, if an electron gets excited up to that level, it's going to fall back down. And so it could fall there or there. And so it could give off different distinct colors associated with the energy levels available in the atoms we're shining the black light on. And so that's what gives us the glow. It absorbed ultraviolet photons, and then it gives off visible photons as the electrons fall back down. Fluorescence happens in maybe 10 to the minus ninth seconds between absorbing the first photon and emitting a photon and falling back down. So it's a very short-lived process. It absorbs the photon, goes to a higher energy, and says, this is unstable, falls right back down to another energy level. And it could fall all the way back down. The reason I didn't write falling all the way back down is because we wouldn't see that, because that would be the same ultraviolet color. So that's what fluorescence is. Fluorescence, it absorbs light, de-excites. Metastable states is another ball of wax. Metastable means I have an energy state that's kind of stable. So now here it shows I pumped something up to an excited state. So I had a photon with energy high enough to raise the electron from the ground state to this state. And it typically stays there. This says 10 to the minus 7 seconds. So that's still very short. It's not 10 to the minus 9. But it very quickly decays down. But if it decays, it could decay back to here, or it could decay to here. But if it decays to here, this is metastable, which means that it has a lifetime that's on the order of milliseconds, a much longer lifetime there. So if I have what we call complete pumping, if I excite all of my electrons up to the excited state, so I have none down here in the bottom, then after the pumping, I'll end up with all my electrons in this metastable state. And that's an important thing for lasers. But first, just make sure we understand metastable states. Lifetime on the order of 10 to the minus 3 seconds before it decays. And we call this decay, when you had a metastable state, phosphorescence. So phosphorescence is decaying from a metastable state, and it's going to then have a bit of a glow. And, we have 10 to the minus 3 seconds. It could be longer. It could be a second, or it could be hours. And so we have some things that are, quote, glow in the dark. They glow in the dark because you have light shining on them. For instance, you have a room light, and that room light is photons that range throughout the visible spectrum. And those photons will excite atoms to higher energy states that are metastable with lifetimes that might be on the order of an hour. And so when you turn off the lights, you have all of these electrons in excited states, and over a course of an hour, maybe half of them decay. And when they decay, they give off visible light, and so you see it glowing for an extended period of time after you turn off the lights. So that's how glow-in-the-dark things that you buy today work. Now, I said that you buy today because back in the day, you could get a watch with a glow-in-the-dark dial, and it doesn't matter how long it's been in the dark, it's still glowing. Now, think about that just for a second. If it's glowing, that means there's energy coming out. So where did that energy come from? Doesn't matter how long, so it's not phosphorescence. It's not that it's excited and had a long lifetime and decided to a metastable state. That can't be it. Well, what they did is they used radioactive materials. They put something like curium in their paint. Why curium? Because it's radioactive and it's constantly giving off high energy radiation. And then they have some phosphors, things that are going to have a metastable state, that absorb that radiation, and with their long lifetimes, it smooths things out, and you just get a nice glow until the curium is no longer giving off any energy. Well, that curium is going to be giving off energy for, I haven't looked up its half-life, but hundreds or thousands of years. So these things will glow for hundreds or thousands of years. So as far as we're concerned, that's going to be permanent glow in the dark. Not just, ooh, I have to shine my flashlight on it and then it glows for a little while. It'll glow forever. But there's the downside, it's radioactive. And I was told that they hired people to very carefully paint onto military equipment glow-in-the-dark paint. And a common thing to do was to wet the brush by rubbing it on your tongue. And then a lot of people got tongue cancers because they were putting radioactive material on their tongue, which then is giving off high energy radiation. And the high energy radiation, as we'll learn in our lectures next week, can damage tissues and cause mutations, and then in the end, cancer. Okay, so what was the point of this slide? Metastable states and phosphorescence. Metastable states are energy states that are long-lived. They don't immediately decay when you put an electron in that state. They will wait a while and then decay. So in order to make a laser, now a laser is light amplification through stimulated emission of radiation. So light amplification through stimulated emission of radiation. That's what laser stands for. It's an acronym. And for a laser to work, you need to have electrons in a metastable state. So they're just waiting around, and then you have something we call stimulated emission that makes them decay. You have to have a second thing there, a thing called a population inversion. Population inversion means you have more electrons in metastable state than in lower state of transition. Which would be in this picture, the ground state. The reason for that is when I have a photon that goes from the metastable state down to the ground state, if there is an electron out there in the ground state, it can absorb that photon and just go right back up. But that doesn't give me any light coming out. That light was immediately absorbed. And so for the laser to occur, I need to not have that absorption back up. And the way we achieve that is by making sure that we have a depletion in the bottom state. So the kind of laser that I'm familiar with looking at its diagram is this one here. There's a 4-level system. So notice here the pumping, we call this pumping the excitation. You pump it up to a higher energy state, and then it comes down to that metastable state. You're not pumping directly to the metastable state. And there's certain reasons for that we won't go into. And then you have a metastable upper state and a non-metastable lower state. So that means for any photon that goes from the metastable down, it's going to immediately fall down to the ground state. And so you're always going to have virtually no electrons hanging out in the lower energy state. Hence, you have a population version that's very easy to maintain. You don't have to have complete pumping. You don't have to have all of the electrons pumped out of the ground state for this laser to work, because the metastable upper state and the lower state not being metastable. So population version, higher population. So if we were talking about people, we might say we have 1 million people in this state and we have 10 people in this state, which means that just following the odds, only about, with the numbers I use, only about 1 in 100,000 of your emissions that are produced would be absorbed back. But we can live with that. So how does stimulated emission work? Remember, laser, stimulated emission. Stimulated emission, the way I always like to think about this is with people in a swing. You only have a certain frequency you can swing in that swing, right? Swings don't just have any old frequency. You can have different amplitudes. You can swing with bigger energies, but it's always the same frequency. So if you have somebody pushing you with the right frequency, you can absorb it and gain energy. Well, we have something that's a little different here when we talk about light emission. So we have a metastable state that decays to the ground state. And so we have, it's a long time, let's say 1,000th of a second, and all of a sudden, spontaneously, one of these electrons that was raised to the higher state by our pumping falls down. It gives off a photon. Well, that photon comes along to another electron that's in the higher state. And let's just think about what it means for radiation to be absorbed or not absorbed. The radiation is absorbed by actually making the electron oscillate, because you have a certain frequency in this wave. And so it makes the electron oscillate because you have an electric field, and the electric field is oscillating. The electron has a charge, so it has a force that's moving it back and forth. That's how you absorb energy. But if this here has the ability to decay, to give off energy, you make it oscillate at the frequency where it gives off energy, and it will spontaneously, so we have the one that came in, it keeps going because it's not going to be absorbed, it doesn't have an available state up here, but it gives off its own energy and makes an identical photon because it was oscillating with the photon. It was oscillating in sequence with that photon. And so it gives off a second identical photon. And so those two identical photons come here, and they cause another one. So you now have 3 identical photons. And each time they come to another electron in the metastable state, it causes it to give off an identical photon. So just like we will study exponential growth with nuclear reactions, you probably have seen very good examples of exponential growth with the COVID-19, the coronavirus. But we have an exponential growth in the number of photons. And so when we put that into a laser, here's the design of a laser. So here's the back of the laser. You have a totally silvered mirror. That means it's 100% reflecting. And up here you have a partially, so that's like 99% reflecting. And we have all of these atoms here, and spontaneously the atoms will decay. And notice it shows this one decaying and the light comes up this direction. Well, that light's just lost. It's not going to be part of our laser. And so we have a bunch of light that was just lost. Any of these arrows that are going off at angles, that's just lost. And notice we had some amplification here, but it's still lost. Just a little amplification on its way out. But then if you have one that's going straight this way, it's not lost. It hits the mirror, and then it's going to reflect straight back. Hits this mirror and reflects straight back again. And so if it's perfectly aligned with those mirrors. So imagine this. These mirrors have to be perfectly aligned. Aligning a laser is not simple because you have to get that alignment so exact. Believe me, experience there. But if you have this aligned just right, this light that's lost will pretty much be insignificant compared to the light that's magnified as the beam travels back and forth. And each time it gets to the front surface, 1% or so of that beam comes out. Because of the alignment, that beam is coming out in only one direction. And the beam's width is limited to that width. So that's how we get a collimated beam. And it's coherent, it's all in phase because you had one initiating photon and then all the rest are identical to it. Now, I talked about wave trains. How do you get more than one wave train? Well, we have all of this light bouncing back and forth, but we could have another particle here that gives off its light in the right direction. And so that's going to go back and forth and get bigger and bigger. And that is not necessarily coherent with the red because it started from a different atom initially. And so that's how you have the different wave trains. The blue wave train will all be coherent. The red wave train will all be coherent. And that's how we make a laser. So now if we follow through the pictures in the sequence, it shows now we have lots of back and forth, and it shows some emission. Now what I did here, this is called a continuous wave. Also known as a CW for continuous wave laser. So the continuous wave, it's constantly putting out a laser beam. You can also make a pulsed laser. This picture looks like a pulse laser. Well, a pulse laser you have virtually no front reflector at all. You just have something that pumps this up. A bunch of energy is dumped in to pump the electrons up. And then you have just a single pulse that it produces as they come out. That's a typical way of making a pulse laser. Another way you can make a pulse laser is to actually make a front surface that that is going to change to allow light through, and so you can control the time of the beam. We're not really concerned for our case about the pulse laser. We just want to know how the laser works. So the continuous wave laser, this explanation here, is really what you need to know. Now here's a practical example with a helium neon laser, HENI for short. So helium neon laser, you have about 10 helium atoms for every neon atom. And you have this pump that is going to pump helium, notice it's helium here, pumps helium up to 20.61 eV. Now let's think about what's the wavelength of a 20.61 electron volt photon. Well, we know energy is equal to Hf, which is Hc over lambda. And Hc has a value of 1240 nanometers times electron volts. So that means if I solve for wavelength, wavelength is equal to, I'm going to put 1240 instead of Hc, 1240 nanometers times electron volts over the energy. So if I take 1240 and divide it by 20.61, I don't have a calculator handy, so I'm going to do it divided by 20 because I can do that in my head. If I divide 1240 nanometers times electron volts by 20 electron volts, well, actually, I have my phone. I'll use my phone. I'll get the answer right. So putting my numbers in, 1240 divided by 20.61, and that's equal to 60.16 nanometers. What kind of light is that? Is that visible, radio, microwave, ultraviolet? Ding, ding, ding. That's ultraviolet. Very high energy for the pumping. Now the helium interacts with the neon and has a transfer of energy to the neon. And so it transfers energy to the neon. And see, you can see down here, excited helium atoms easily de-excite by transferring energy to neon in a collision. And you end up with the neon having a 20.66 electron volts above the ground state energy. Actually went up a little, right, because of the collisions. But then the energy states of neon, this top one, this 20.66 electron volt energy state, is metastable. And so, excuse me, the neon atoms stay in that heightened energy state until something causes them to fall to a lower energy state. And they will fall down just 1.96 electron volts. And then they have a short life to standard state, and they fall down the rest of the way. So this one here, if you take 20.66 minus 1.96, that's 18 point, doing math, that would be 20.6 minus 1.9, 18.7 electron volts, 70 electron volts. Well, we can once again calculate the wavelength of that, which is 1240 divided by, well, I'm going to check and make sure I did my math right. I mean, anyone should be able to do that math right, but I am not feeling confident in myself. Okay, yeah, that was right. 1240 divided by 18.70. So that's a 66.31 nanometer radiation. Well, that's once again very ultraviolet. They're going to have a filter on your helium neon laser, and all you have to do is use glass. Glass will absorb that. So we don't have that very damaging ultraviolet radiation coming out. And what we do have is this radiation that's visible. So if I take 1240 and divide the 1.96 electron volts, that gives us equals 632.65. I'm just going to put 6 nanometers. Well, I'll put 6.5. 632.65 nanometers. Now, I only have 3 sig figs here. So I would put 633 nanometers to within the sig figs I'm using. And so that's the wavelength of a helium neon laser, because that's the energy difference between the metastable state and the transition that it goes through. Now, you might ask me, why doesn't it transition all the way down here? Well, from our last lecture, we learned that there are selection rules. Transitions have to have delta L equals plus or minus 1, because the photon carries an L of 1. And likewise, we have to have delta M sub L is equal to 0 or plus or minus 1. So we have those restrictions that make it so some transitions that should be allowed aren't. And so that's how we only have that decay. Now, some applications. Application number 1, if you have a detached retina, if you look in the picture here, we have a little blister, if you will, where the retina has broken free. And so what they do is they use a laser to spot weld. And yes, weld is the right term. In fact, when I finished graduate school, I was considering going to Japan and doing research on laser welding, using holograms to do laser welding so you could do welding very quickly and accurately. So the laser is depositing energy. The energy heats things up and fuses stuff. So that's one application of lasers. You've seen a lot of them. Here's another one. I probably have been in this very location. It's, I think, the National Ignition Facility there at Lawrence Livermore National Laboratory. This is inertial confinement. It's a way of causing fusion. They have a little target, and that target contains hydrogen, deuterium, tritium. They have different mixes to try to optimize. And then they have a very, very strong laser, strongest laser in the world, I believe, that focuses in all directions. So you can see in this picture that they have all of these ports for the laser beams to come in. Will highlighting show? No, highlighting won't show it at all. You know, I don't have any colors that are going to be very, but all of these places where laser beams come in, and they're all focused right at one point at the center. And they focus all of those laser beams on this. And like I said, those laser beams are enormously strong. They start with one laser like this, except for it's a pulse laser. And then it goes through a bunch of amplification stages. What's the difference in the laser and the amplification stage? Each amplification stage is pumped externally to raise the electrons into the excited state that was used in the laser, but then it doesn't have mirrors. So it just comes in one side and goes out the other. So these amplification stages, you have a strong beam that comes in, and basically all of the electrons in here are excited and all of them de-excite. And so your energy goes up, maybe let's say 1,000 times for each one of these stages. They have like 100 stages on the line. They split it up. So it really is incredible to see. It's like a huge warehouse filled with the laser beam and these amplification stages to focus it all. So they can put all of that energy in this little packet, and then that little packet undergoes nuclear fusion and releases energy that's greater than the energy. They've actually reached break even, I'm pretty certain, greater than the energy that they put into creating that laser beam. The energy used by this is enormous. The goal is to try to find a way to make controlled fusion so we can make fusion power plants. We have fission power plants right now, nuclear fission power plants, but they have some drawbacks. The biggest drawback is that you have radioactive material that you start with and radioactive material that you end with. And so you have to find a way to dispose of that radioactive material. The nuclear fusion would have essentially a radioactive water, but you have, tritium. It exists in the ocean, and they would just take that tritium and use it. And when they're done, they have nothing radioactive. So you really don't have the waste problem, the how do you get rid of it problem. Another example of lasers is in holograms. So this is an example of what you see on a credit card, a little hologram of a bird. I think it's a dove, but I don't know. So let's look at how holograms are made. There are different types of holograms, and this is the only one we're looking at. So in this hologram, you have a coherent beam of light. In other words, you use a laser. And that coherent beam of light, then, you split it in two paths. Now, in this case, they used a mirror here to make one path like this, and then they just let the rest of the light come through and hit their object, which was a dinosaur. And the light that hits this dinosaur reflects off, and some of that is going to hit this photoplate. And since this light was coherent, it was all in phase, you have a fixed phase relationship. And depending on the distance from here to here to here, and the distance from here to there, well, I should try and make it in the same place, you'll have constructive or destructive interference. And so this photoplate records an interference pattern. Now, this is complicated because we have a lot of different light paths, and it's all coming together, but it creates an interference pattern. And so then you take that photoplate that has its interference pattern. So from what you've seen, that would be things like this. But of course, it's much more complicated. It isn't going to look anything like that. And then to view it, you just put in another coherent reference wave And that light, when it hits the diffraction pattern, then it's going to diffract. And if you look in this direction, you're going to see back here extrapolated, and it will make a virtual image. Or if you look from out here, it would actually make a real image. And so you have these images that are made by reconstructing the light rays that made this diffraction pattern, because light works the same way forward and backward. You basically have the diffraction pattern reproducing the object that made the original diffraction pattern. So we call this a transmission hologram. So the only kind we're looking at, it's the simplest one to make. That's the one that you potentially could have done for a lab project. Now I just have a few more odds and ends. Why is m sub L between L and minus L? Well, we have two equations. Total angular momentum is equal to the square root of L times L plus 1. It's a plus sign. H bar. And then in some arbitrarily selected z direction, the component in z direction is m sub L H bar. So what this means is you can only have a specific angular momentum. So if I draw my total angular momentum, it goes in my picture around like this. It should be a semicircle, a half circle, with a radius of square root. And I'm just going to choose number. Let's see, that's 0, 1, 2. So I'm going to say L equals 2 for this picture. So square root of 2 times 3, 2 times 3 is 6, square root of 6, H bar. So that's what the radius is. But then the actual component in the z direction is 0 or H bar or 2H bar. Or it could be minus H bar or minus 2H bar. And so what this means is there is a certain angle between the z-axis and my actual angular momentum. And so in this picture, it shows theta 1. Now this one here is L equals 2 is this picture. This picture here was L equals 1. So the pictures don't correspond. But you have the angle from the z-axis to the upper one, to the middle one, to the lower one. And so we'll do the same thing here. If I have this one here, m sub L equals 2, then I have this angle, theta for 2, and I know the hypotenuse is square root 6H bar, and the adjacent side is 2H bar. So hypotenuse and adjacent, that's cosine. Cosine theta 2 is adjacent, 2H bar, over hypotenuse square root 6H bar. Notice the H bars conveniently cancel out. And so cosine theta 2 is equal to 2 over square root of 6. And if I get out my handy-dandy calculator, and I have to be a little more handy-dandy now, that would be square root of 2/3. I think that's right. 4, 6, 2 divided by 3 equals square root. Then I need to do the inverse cosine of that. That gives me 35 degrees. 35.3 degrees. That's the closest you can get to having the angular momentum aligned with the z-axis, which seems crazy. Because if I have a magnet and an external magnetic field, we know that they align together. And now we're saying this magnetic moment, or this angular momentum tells us the direction of the magnetic moment. And if I put an external magnet, the z direction is the direction of the external magnet, it can't align. That just seems crazy, but that's what quantum mechanics says. Now, What if I tried to use m sub l equals 3 here? If I tried to use 3, I would have had cosine theta 2 is 3 over square root 6. But 3 over square root 6 would be the square root of 9 over 6, which is, square root of 3 over 2. That's bigger than 1. So that wouldn't be possible. You couldn't have an angle if you had m sub l equals 3. So there is a practical limitation. That's why m sub l has to be between plus and minus l. If it was bigger than plus or minus l, that is, if m sub l is equal to l plus 1 or m sub l is equal to minus l minus 1, then you don't get an allowed angle. Now, what does this mean then if it doesn't align? We know that for lowest energy, the L sub z should align with the z-axis. It can't. And what actually happens is we set up a precession. We set up a rotation where the angular momentum orbits around, keeping the z component constant, and the x and y components are constantly changing. And so that's what these circles are indicating is it's precession, as we call it. It's going around, just like a top, when it spins, it goes around the circle as it's falling down. So there's a practical explanation of what the m sub l tells us and why m sub l has to be between minus l and plus l. That is the end of this lecture. Have yourself a great day.